In this video, we're going to be looking at core practicals 9A, 9B, and 10, which are part of the Unit 6 Edexcel course for A2 Chemistry. So we're going to start off by looking at core practical 9A, which is rates of reaction using the Titrimetric method. Now, 9A and 9B both come from topic 11, and they are all to do with kinetics. They are just two slightly different ways to carry out the experiment to find a rate equation. So when we're using the Titrimetric method, where this is a version of a continuous method, and the objective is to determine the order of reaction with respect to a substance using a concentration time graph. So this is data from one experiment where the concentration of one substance is followed throughout the experiment. And we then process that by plotting the data, and then we calculate its half-lives. And we look to see what the pattern is for the half-life. And if the half-lives are constant, then the reaction is first order. So for apparatus, well, we're going to be using propanone, sulfuric acid, potassium iodide, thiosulfate, and starch. We're going to use sodium hydrogen carbonate to quench our reaction. We're going to need things like a beaker, graduated pipette, conical flask, and of course a stop clock, because we are going to be timing this particular reaction. For safety, of course, we're going to need eye protection. Iodopropanone is irritant to the eyes, so it can cause your eyes to water. So when we are disposing of it, we need to make sure that we rinse it with lots and lots of water. Sodium thiosulfate can release sulfur dioxide, and propanone is very flammable, so we make sure that the room is extremely well ventilated. And of course, we want to avoid skin contact with any of our reactants or products. So how do we carry out this experiment? Well, we have our aqueous propanone, and we add sulfuric acid of that volume and concentration into our beaker. So we start with the propanone and then we acidify it. To that, we then add iodine solution, and we start the clock, and we make sure to swirl or to mix the beaker so that we get a complete mixing of all of our substances. We use a 10 centimetre cube pipette to withdraw a sample, and we then transfer that to a conical flask. To that flask, we then add sodium hydrogen carbonate, and this is to quench the reaction. In other words, to stop the reaction. And then we record the time at which the sodium hydrogen carbonate is added, and that should be recorded when we have added half of the pipette amount. Once we have that sample, we then want to titrate the iodine in the conical flask with our sodium thiosulfate. When it goes a pale yellow colour, we add the starch, and then it will go from a dark blue colour to colourless, and that is when we have our final titer, so making sure to use our starch indicator. And then every 5 minutes, we want to withdraw a sample, and then we repeat steps 4 and 5 where we quench and titrate it until we get a specific number of results, probably 6 or 7, so that we can then plot these onto a graph. Now this is our equation where we have our acid reacting with our iodine, and I'll put a link to this YouTube video in the description, and this is just how we actually carry out the experiment, so you can see it being physically carried out. As I said, the purpose of the sodium hydrogen carbonate is to quench the reaction so that we can titrate it, and that allows us to measure the concentration at a very specific time. If we don't quench the reaction, then the reaction will continue to happen, and then we can't measure our concentration. So it's very important that we do that step. What we can then do is we can then plot the results for the experiment into a concentration versus time graph, and you can see here that we have a nice negative straight line, and that tells us that this reaction is actually zero order with respect to the iodine. And this is the fact that the half-life of the reaction is independent of the concentration, therefore it is constant. Okay, so iodine is zero order with respect to this reaction. Now this particular reaction is actually then first order with respect to propanone and the acid catalyst, and we can show that in our rate equation here. Okay, what this rate equation tells us is that the rate determining step contains one molecule of propanone and one hydrogen ion. The iodine that is part of this particular reaction must be involved in a subsequent step, but it is not part of our rate determining step. So remember, our rate equation is our rate determining step. So we're going to look at a past paper question just to go into a little bit more detail with this to show the actual reaction of this particular titration. So we've got the iodine reacting with the propanone, and we have our 6 steps here. So this is pretty much what we just said that we do. So we have our iodine in a solution, we add into our propanone and our sulfuric acid, we have our mixture added and we start the clock, and then we pipette our sample, we quench it, and then we titrate it. So part A looks for suggesting a solution which could be used to stop the reaction in step 4. Well, a solution that can be used to quench the reaction. There are 2 key ones that you would probably use. So we're going to have sodium hydrogen carbonate, or sometimes you may use potassium hydrogen carbonate, but generally sodium would be the one that we would go for. And part B, at what point in step 4 should the time be recorded? Well, we mentioned that before. That is when half of our reaction mixture has been pipetted into the quenching solution. Okay. So then we want to calculate the concentration in moles per decimeter cubed of the iodine solution immediately after mixing with the acidified propanone. So we can see in step 1, we have 50 centimeters cubed of a solution, and that gives us a concentration of 0.02 moles per decimeter cubed. Now we can see that we then add 25 centimeters cubed of propanone and 25 centimeters cubed of sulfuric acid. So we're adding in an extra 50. That's going to put our solution up to 100 centimeters cubed. Now, if we are doubling the volume of our solution, we must then be reducing our concentration. So in this case, because we're doubling the volume, we must be reducing the concentration by half. So by half would bring us down to 0.01 moles per decimeter cubed. The iodine that was present in the 10 centimeter cube sample after reacting for 70 seconds was then titrated, and we're using 0.01 sodium thiosulfate, and we get a titer volume of 18.5. We want to calculate the concentration of iodine after the 70 seconds and there calculate the mean rate change of iodine. So this is put into 2 parts. So you can see that it's split into 4 marks. We have 2 marks for calculating the concentration and 2 marks for calculating the rate. So if we look at the concentration first of all, well, we can work out the number of moles of the sodium thiosulfate. And that is going to be concentration times volume. So we have 0.01 times 18.5 divided by 1,000. And that's going to give us an answer of 1.85 times 10 to the minus 4. Now you can see based on our coefficients, we have a 2-to-1 ratio for the sodium thiosulfate to the iodine. Therefore, we take the 1.85 times 10 to the minus 4 and we divide it by 2 to get 9.25 times 10 to the minus 5 moles of our iodine. And then we need to convert that into a concentration. So concentration we know is number of moles divided by volume. So we have 9.25 times 10 to the minus 5. And we used a sample of 10 centimeters cubed. So that becomes 0.01. So we have a concentration of 9.25 times 10 to the minus 3. Now that's the first part sorted. The second part is then looking at the rate of change. And we know that to calculate a rate, we have a change in concentration divided by the change in time. And we are told that the time is 70 seconds. And we know from the previous question, if we just go back, that our concentration was 0.01. So we have went from, so our rate is going to be 0.01, take away 9.25 times 10 to the minus 3, all divided by 70, which is going to give me a value of 1.07 times 10 to the minus 5. And of course, it says include units. So my units in this case are going to be moles per decimeter cubed per second. And that is our final answer. So further experiments show that the rate equation is this. Now we've just seen that a few minutes ago. So the diagram shows typical results of the original experiment, and the volume of the sodium thiosulfate, as we can see here, is proportional to the concentration of iodine. So whatever sort of graph we get for the volume of sodium thiosulfate, we're going to get for the concentration of iodine. So we want to use the rate equation to explain the appearance of this diagram. Okay. So iodine does not appear in the rate equation. So the reaction is zero order with respect to iodine. Okay, now that would get you 1 mark because we have to then use that to explain the appearance of the diagram, and this shows that the rate is constant in the diagram. So because the iodine is zero order and it doesn't affect the reaction, it therefore does not affect the rate. Okay, so our rate is constant in this diagram. The experiment was repeated, and the only change that was made was that we used 25 centimeters cubed of 0.5 moles per decimeter cubed propanol. So we are halving our concentration of propanol. We want to now add a line to that diagram to show what results would be obtained in this repeat experiment. So let's just go back. So if this is our experiment, well, if we're going to halve our concentration, that is going to have an effect on our rate. And what actually happens is we get something that will look like that. So we start at the same point of the volume of sodium thiosulfate, but we have a slightly less negative gradient. And we want to explain the difference in the results by using our rate equation. So our rate is half of the original experiment. And this is because propanol is first order, or the reaction is first order with respect to propanol. We can't simply say that propanol is in the rate equation because we're already told that. We have to understand that it is first order with the reaction is first order with respect to propanol. So our rate is proportional to the concentration of propanol. Meaning if we half the concentration, we're going to half the rate. If we quarter it, we're going to quarter it, or double. You can see the pattern. The titration was carried out using an indicator. Name the indicator, state when it is added, and give all of the colour changes that are involved. So 3 parts to this. So the first part is the indicator is starch. The second part is when do we add it? Well, we add it when we get a pale yellow colour of our substance. And then what should we see? Well, we should see the end point going from blue-black to colourless. That's when we would stop the titration and we would take our volume. So you can have a look at the mark schemes here as well, and all of the information for these questions that are from the June 2018 paper. So let's look at practical 9b. So this is another way that we can use to calculate a rate of reaction, and this is using the iodine clock. So this clock reaction is used to find the order of reaction with respect to either iodide or the peroxo disulfate ions. So clock reactions are slightly different, where they involve setting up individual experiments and we change the concentration of one reactant at a time. So rather than following a continuous method where we're constantly taking samples, we do individual discrete experiments. And we can then plot a graph of 1 over T versus the concentration. We can then look at the shape of the graph, and then that tells us the order of reaction. So these are our two equations where we've got our hydrogen peroxide reacting with iodide, and then the iodine that's formed in that reaction reacting with the thiosulfate, and then we carry this experiment using a starch indicator again. So I will put this link to the method into the description. You can just see it's just a way to actually show you how to carry out the experiment. So when we have these reactions, so the hydrogen peroxide is reacting to form the iodine, and the iodine then reacts immediately with the thiosulfate in the second reaction. That's what these equations are describing. When the iodine produced has reacted with all of the thiosulfates that are present, remember they are going to be your limiting agent, we have excess iodine remaining in the solution, and the reaction then suddenly forms a blue-black colour. So we have starch in these mixtures, and when this reaction is limited by the thiosulfate, that's when we see our colour change, and that's when we would stop our clock, and when we can use that time to have a look at our rates. So we're going to use a lot of the same kind of overall apparatus as the Titrimetric method, because we're using the same chemicals. So we have our sodium peroxo disulfate, our potassium iodide, sodium thiosulfate, our starch. This time though, we're going to be using measuring cylinders, pipettes, and we're going to be using 9 beakers. We have 9 different solutions that we would use here. And safety-wise, of course, eye protection and making sure to avoid skin contact. So we're going to measure out 10 centimetres cubed of potassium iodide into a small beaker. We then add our sodium thiosulfate, and then we add 10 drops of our starch to act as our indicator. We measure out the 10 centimetres cubed of the sodium peroxo disulfate, and we pour that into the mixture, and then we start our stop clock. As soon as we get that blue colour appearing, we stop the clock and we record the time. We then repeat all of these steps using different volumes of our sodium peroxo disulfate and our potassium iodide. The only thing that we need to make sure is that our total volume is always 25, and we do that just by topping up with distilled water. So you can see that we have various different solutions here, and we're going to vary either our S2O8 ion or our iodide ion. And so we end up with 9 different samples here, and that we can then have a look at. And of course you can see the water changing here, just to make sure that we keep a total volume of 25 centimetres cubed. So the results for this experiment would then be plotted into a graph that is 1 over T to the concentration, and the rate is proportional to 1 over time. So that would be like a rate concentration graph, and depending on what shape we get, we can determine our order. So if it's 0 order, we should see no change at all. We should see just this flat line here. If it is first order, we get a nice straight line. If it is second order, then we see this curve, which is a bit of a problem. So what we would actually do for second order is we would plot this 1 over t to a squared, and if we did that, we should get a nice straight line, and that tells us that we have second order or first or zero. So the rate of the reaction for this particular experiment is proportional to 1 over time, and we can then use the changes in the rates and the concentrations in our graph to deduce the order with each reaction. So we have to look at how the rate changes. If the rate doesn't change when the concentration of a reactant has doubled, then the reaction order is 0. Okay, so we have no change. If the rate doubles as the concentration doubles, then it is first order. If the rate quadruples when the reaction is doubled, then it is second order. So this is all about comparing sets of results. And you look at what was the rate, with this particular experiment, compare that to when we've changed a concentration or doubled the concentration of one of our products, and then what has happened to the rate. Some errors that could come up here is that we get some inaccurate timing of the appearance of our blue colour. So we could time simultaneously and then use an average value, because sometimes our reflexes may not be fast enough in order to stop the clock at the exact time. And adding the starch is going to slightly increase the volume, which can affect the concentration of the reactants. So they can change slightly over time, because what you may put in 10 drops from the first time may be slightly different to the 10 drops at the second time, but this is very, very minimal, so it shouldn't have too much of an effect. Now, I wasn't able to find any past paper questions from Unit 3 on this method. They typically focus on the Titrimetric method. When it comes to the iodine clock, that tends to come up more in Unit 2, because it is the actual processing of the data to show how you know it is first, second, or zero order, as opposed to how do you actually carry out the experiment. Whereas for the Titrimetric method, that's a good question to ask, how you actually carry it out. So core practical 10 is how we find the activation energy. Again, this is linked to topic 11. So the experimental objective is to use the Arrhenius equation to determine the activation energy of a reactant. And the Arrhenius equation is given here. You're not expected to memorise this. You can be given that, you will be given that in an exam. And it is linked into our equation of a straight line, which is y equals mx plus c. So our lnk is our y, our EA over r is our gradient, 1 over t is our x, and ln A would be our y-intercept. So we can plot ln K against 1 over t, and then we can use the gradient to determine our activation energy. So how do we carry out this experiment? Well, we're going to be using a phenol solution, and as well as a bromide-bromate solution. We're going to need some sulfuric acid and methyl red indicators, as well as beakers, boiling tubes, pipettes, thermometers, and stop clocks. Safety as normal, wearing eye protection and suitable chemical resistant gloves, and making sure that we don't inhale any fumes that might be produced. So how do we carry out this experiment? Well, we pipette 10 centimetres cubed of our phenol solution and our bromide-bromate solution into a boiling tube, and then we add a few drops of our methyl red indicator. We put 5 centimetres cubed of sulfuric acid into a different boiling tube. We create a water bath at 70 degrees Celsius and then put the test tubes into it. We then leave that for a while to make sure that they get to that same temperature, and then we combine the two mixtures and start the stop clock. We leave the boiling tube until the colour of the indicator disappears, and when that happens, we stop the stop clock and we note the time. We repeat this same experiment at a number of different temperatures, and we get values for time for each of these. We then convert our temperatures into Kelvin, of course, and then calculating the reciprocal, which is just 1 over T. We take the natural logs of each temperature, and the K is equal to the constant or the time and we take the natural logarithm of that, and we can then plot a graph of ln k against 1 over t. So what does that actually look like? Well, you can see here that we have our temperature in Kelvin. We've taken the reciprocal here. We have our time in seconds, and we take the reciprocal of that as well. And then we take the natural log of t, and we plot this natural log here versus our 1 over t. And we can then use that to determine the gradient. Now, the gradient should always be a negative number, and the gradient, of course, is, remember, is measured by y2 minus y1 over x2 minus x1, or the change in the rate over the change in time. In that particular example of our graph here, we have this as our gradient, so minus 5,680. We can then substitute that into our EA over R and determine that the activation energy for this reaction is 47,200 joules per mole. And of course, we always want to put that into kilojoules, so we divide it by 1,000 and we get an activation energy value of 47.2 kilojoules per mole. Now again, I was not able to find past paper questions from Unit 3 for this particular topic. It tends to be in Unit 2, asking you to either plot this graph or do this calculation to determine EA, as opposed to it being the actual practical side of it. However, remember, those are all in the old specification, so in the new specification, this could come up. So just make sure that you are aware of how to carry out these experiments. I hope this video has been useful explaining core practicals 9 and 10. Check back later for videos on the remaining core practicals for Unit 6. If you have any questions, please feel free to leave a comment below, and we hope to see you back on the channel.